Next speaker, Professor Saugata Basu, on the homology of symmetric semi-algebraic sets.
Thanks, Jim and Jim, for organizing, inviting me. So I realized from the morning session that this session is kind of quite different topic, looks like. So just to be honest to the main theme of this conference, namely ordered algebraic structures, I should say that in my talk there will be two ordered algebraic structures, which implicitly will be important, but it will not be visible from what I'm saying. But they will be like the reals, of course, real closed fields are ordered fields. And then we'll be talking about symmetric, and the symmetric group, finite symmetric groups, have an implicit, so there's a Bruja ordering on the, so there is a four-set structure on the symmetric group, which also plays a role, but will not be visible. So at least there are two ordered structures in this talk. And the reason I wanted the blackboard was, before I begin, maybe I should explain. So semi-algebraic sets, Ali has already said what they are. And we're talking about homology. And for the purpose of this talk, you can just imagine that the real closed field is R, and our semi-algebraic sets will be compact semi-algebraic sets, and you can take homology to mean singular homology if you want. But then we'll also want these sets to be symmetric. So maybe the only main example that we can keep in mind is very simple one. Take the polynomial which defines the circle. So that's it defines circle. All this V. And it's subsymmetric polynomials. So that means that it's stable under the permutation symmetric group S2, which is the same as saying that it's stable under reflecting along this line. And then the homology of this set. Well, you don't need to remember too much about homology, but one thing is that we are going to talk about homology with rational coefficients or coefficients in a field of characteristic 0. And if this set has two non-zero homology, okay. So, and you can see that they are both isomorphic, one-dimensional. But now the reflection or the action of the symmetric group is going to, so I better use so that so this map reflecting acts on these vector spaces, making these vector spaces into representations of the symmetric group S2. So now if you think about it, so I can now think about these homology groups as representations of as S2 modules. And the action on the H0, which corresponds to connected components of these as connected, is trivial if you want, because you can compute of the circle into two zero cells and one cell. And you see that the action keeps the zero cells to be stable, right? So from the point of view of as an S2 module, this is the one-dimensional trivial module. And maybe I should remind you that so there is a classification of the irreducible modules of finite symmetric group. So they are parameterized by partitions of n, so partitions of 2. And the trivial one is the one corresponds to the trivial partition into just one part. But if you take the other one, so now if you think of these as an oriented cycle, then if you flip it around the S1, S2, you see that the orientation changes. So it changes sign. And so as an S2 module, this is what's called the sign representation. And the sign representation corresponds to the transpose of this partition, namely partition 1, 1. So that's all the talk is going to be about, that we are going to talk about symmetric semi-algebraic sets, and we are going to look at isotypic decomposition of the homology as SN modules and see that they give us some more useful information than just in the homology. So now,
Sharing screen.
are there any questions about? How does it work?
Didn't work for me. It turned on.
No, it's on.
Just hit the space bar.
Okay, so that's a very optimistic list, but. Okay, so most of this definition is already carrying over from Ali's talk, so P semi-algebraic set, and maybe only the new one is this one, that if we insist that all the inequalities that appear in the formula are weak inequalities, then the semi-algebraic set is closed by definition, and we'll call such a semi-algebraic set a P-closed semi-algebraic set. And now there are very, by now, quite classical results, which tell you that if you have a P semi-algebraic set, where you have a bound on the cardinality of P and on the degrees, then the homology groups of this set cannot be two, or you can bound it uniformly in terms of these two parameters, and of course also n. And so the origins of such a result goes back to the work of Oleinik and Petrovskii in Soviet Union, but then they were rediscovered by Thom and Milnor. And then there are various refinements of this. So in the way that I have stated it in this most general version, it's the work of Gabrielov and Borodjov, where there's no assumption of the semi-algebraic set, whether it's closed or not, an arbitrary P semi-algebraic set. But the main thing about this bound, so Pi of S is the ith bet. So we're looking at the sum of the Betti numbers. And this is bounded by some expression which is exponential in n, which is the number of variables. Okay. Otherwise, it's polynomial in S, and that's the context. And this bound is quite, this exponential dependence is not avoidable, because you can easily create a polynomial. Remember, it's a real algebraic set, so you are allowed to take sums of squares. So this is a degree 4 equation, and its 0 is just all the vertices, let's say, of the Boolean hypercube, or points with coordinates which are 0 or 1. And so, of course, the number of connected component is 2 raised to n. So that gives you exponential dependence. Okay, so maybe I skip it. So there is an underlying algorithmic problem of how difficult it is to compute the Betti numbers, and this problem is more or less open. If you can do that in complexity, that's also simply exponential. But okay, let's come down to symmetric, like this example here. So suppose now you have we consider symmetric polynomials of degree at most d. So the subspace of the polynomial ring. And we'll say that semi-algebraic set is symmetric if it's stable under the standard action of commuting the coordinates, but secretly it's the action is generated by reflections about the hyperplanes that in this case there's only one hyperplane. So there's some motivation that various kinds of symmetries occur in practice, I guess. But one thing is that the representation theory of symmetric group is very nice and pretty and is well understood, so it can be used as a test case. And there are certain analogies with what's nowadays called representational stability theory, which I will come back to towards the end of this talk. So, for example, making sense of symmetric semi-algebraic sets in a number of variables close to infinity. So, isotopic decomposition. So, this is what I have already explained in this picture here. But as I said, the action of the symmetric group, if you have a symmetric semi-algebraic set, makes the homology into a finite dimensional SN module. And so we have a canonical direct sum decomposition of these homologies into isotopic components, where each isotopic component is a multiple of some irreducible representations. So these are sometimes called spect modules, and they are parameterized by partitions of N. So here, S2, there are only two partitions of N, and the only spect modules are the trivial and the sign. But already in S3, there is a partition 2, 1, which is neither trivial or the sign. And the dimensions of these spect modules over Q are given by the Frobenius formula, sometimes called the Hooke formula, and that's easily computable. So now, coming back to that bad example of the Boolean hypercube defined by this symmetric degree 4 polynomial. So clearly, as we said, that B0, H0 of Vn is of dimension 2 raised to n, which is exponentially large. But let's look at what happens in the isotopic decomposition. It's a standard exercise that I'm going to skip. But if you take the isotopic decomposition, oh, by the way, I see that I have switched, but from the point of view of SN module, because the permutation group has the good property that the permutation and its inverse are in the same conjugacy class. So, so the dual of our representation is isomorphic. So it doesn't matter whether I talk about homology or cohomology in this setup. So, okay. So, we have an isotopic decomposition. But in this case, the isotopic decomposition is, you can compute it of this Boolean hypercube. And the isotopic components, well, only those appear with positive multiplicities are those for which the partitions have length at most 2. And so it only goes over partitions of length at most 2, and the multiplicity is actually this number. So it's 2 times mu1 minus n, where I'm representing the partition mu as mu1, mu2. So mu1 is bigger than equal to mu2. And you see that these numbers, this multiplicity here is at most n plus 1. And so it's a polynomially bounded. So, but of course, the total dimension is exponential. There are only polynomially many partitions, or n many partitions of at most 2 parts. Each one of them occurs with multiplicity, which is also very small. But of course, some of these, by the Frobenius formula, dimensions of spect modules that get exponentially equal. So this gives you the dimension of S mu for partitions of at most 2 parts, and you can see that this can be exponentially big. So the moral of the story, just to summarize, is that you had this exponentially big homology, but it turns out that it's built out of rather small number of pieces. These are the number of partitions of at most 2 parts of multiplicity, which are also very small. And but of course, the spect modules whose dimensions you can calculate easily are big. So we can ask that how general is this phenomenon, and does it help actually in computing better numbers? And so here's one of our theorems, which kind of even though it looks complicated, I'll explain in a second, which tells you that the answer to those questions are somewhat positive. So if you have a P-closed symmetric semi-algebraic set defined by symmetric polynomials of degree at most d, then most of the multiplicities, and you are looking at the ith homology, let's say for some fixed I, you can think I to be 0, if you want to look at the H0. So for I equals 0, then if the length of the partition is bigger than 2d minus 1, then the multiplicity is 0. So only very few of the partitions of length at most 2d, let's say, can appear with positive multiplicity in the isotropic decomposition. And moreover, there is a polynomial bound on these multiplicities. So that's exactly what was going on here. That there was a small number of pieces, each of small multiplicity. So let me pause here. Are there any questions? Okay, so if you are interested, they are here in these papers. And the work also has some algorithmic consequences, mainly by we are able to compute the Betti numbers in this kind of fixed dimension and fixed degree situation with complexity as polynomial in S and N, the number of variables, exponential in the degree and M. And the main idea is to interpret these multiplicities in the isotropic decomposition in terms of actually Betti numbers of pairs of some semi-algebraic sets of small dimensions. Corresponding problem without the assumption of symmetry, even if you want to compute the small dimensional homology, is extremely hard. Okay, so maybe how much time do we have?
Another 20 minutes, I see, 22.
So maybe I go over some key ideas in this strategy to interpret the multiplicities as decompositions of, maybe we should see some quick pictures on the way. So the first idea is to reduce the analysis of these homology groups of arbitrary symmetric semi-algebraic set to ones which are rather special. And these are called, the terminology, I think, is due to Arnold and Giventhal. They're called van der Monde varieties. And what they are is that you take some level sets of the first few Newton power sum polynomials and intersect it with the Weyl chamber. By the way, in the case of R2, this reflecting hyperplane partitions the R2 into two regions, where in one region x1 is less than or equal to x2, other region where we have the Weyl in common. And these are called, in general, the Weyl chambers. There are two of them here. In n dimension, there will be factorial n many of them. But there's one which you can always fix to be where x1 is less than or equal to x2. This is a Weyl chamber. There are two of them. Oh, sorry. So you take the level sets of the first few Newton power set polynomial, intersect it with the Weyl chamber, and what you get is a semi-algebraic set that they are called van der Monde varieties by Arnold and Giventhal. And in math language, so you look at, by the way, so this should be an n, not a k, but you look at this map, which maps points in Rn to the first d power sum polynomial, and the intersection of the fibers of this map with the Weyl chamber is what's a van der Monde variety. And so there is a machinery which maybe I don't talk about, which tells you, because there's some kind of vibration argument going on, that by using some machinery from algebraic geometry, namely proper base change and Schur's lemma, that it suffices when trying to prove a vanishing theorem, namely that you want to prove the multiplicity of some representation is 0, to prove the same statement or nearly the same statement for van der Waals varieties. So that's kind of something more general. So let's skip it. So let's just concentrate on van der Waals varieties and just believe me that if you can prove such a vanishing theorem for van der Waals varieties, you will be able to prove it for arbitrary semi-algebraic sets defined by polynomials of degree at most b. And then there is a second ingredient. So now we have to analyze van der Waals varieties. And the second ingredient is coming from theory of Coxeter groups. So a Coxeter group is a group generated by reflections. So maybe don't worry about general definitions. In the case of the symmetric group, you can take these, well, symmetric group is generated by these transpositions. And you can think of these transpositions geometrically as reflections along the corresponding walls of the Weyl chamber. So here, there's only one transposition, and the reflection is along its x1 equals x2. But in general, if you look at the general Weyl chamber, then the walls would be x1 equals x2, x2 equals x3, and so on. And so these are called Coxeter elements. And so given such a Coxeter pair, the group and the Coxeter generators, and as some space Z, which would be in fact a van der Waals variety, and a family of closed subspaces, one corresponding to each Coxeter element. And these in our application would be the intersection of the van der Waals variety with the walls of the Weyl chamber. So this is called a mirror structure. And if you have such a object, a space with closed subspaces, you can build, using the action of the Coxeter group, a bigger space by gluing these Z's along these closed subspaces according to the action of the Coxeter group. Now that definition is a bit complicated, so maybe I'll just provide an example of what's going on here. And that picture should understand. So here we are looking at a particular van der Waals variety in R4. So we're looking at the van der Waals variety in R4 defined by the level sets of the first 3 Newton power sums. So X1. So we are looking at in R4 a set defined by setting the first Newton power sum to something. The second one, 2, and the third one, 6. That's what this picture is. So, of course, I can't draw a picture in R4. So this one is a hyperplane, right? And inside this hyperplane, we have so that's a 3-dimensional thing. Inside it, we have a sphere. That's a 2-dimensional sphere. And that's the 2-dimensional sphere. And these 3 now defines a curve in this 2-dimensional sphere, and this curve is shown in blue. And in S4, there is 24 Weyl chambers, factorial 4. So these planes here, x1 equals x2, 3. So they are drawn here. So they tessellate the 2-dimensional sphere into 24 regions. And the van der Waals variety, so the curve given by these 3 equations, is the intersection of that curve with one of the Weyl chamber. So here's, I just drew by hand one of the intersections. So this is the van der Waals variety. So that's the Z. And then it has the subspaces which are intersection of this with the Weyl chamber. But by the way, as you change the level sets, the topology of this van der Waals variety can change. I mean, not of the van der Waals variety, but the blue curve can change. For example, if you take something else, it might look like that. And the thing that one has to analyze is that how does the part, how can you read off the topology of this whole blue curve, this van der Waals, from the part that intersected with only one of the Weyl chamber. So the combinatorics of where it intersects the walls of the Weyl chamber tells you the homology of the blue curve. So there's a formula for doing that. Arnold Giventhal proved that the intersection, if it's non-empty, with the Weyl chamber is always contractible. So it always looks, even though the set itself might become singular, but this part is, it's a wall. Okay, and now this is a theorem from Michael's book, which tells you exactly what I wanted to say, that this thing that you obtain by gluing little blue curves in order to get the big blue curve, the homology as an SN module, again, it should be an N, is given by a formula. So this formula has is indexed by not partitions, but some subsets, by all possible subsets of the Coxeter elements. And there are the spec modules, which are indexed by partition, but there are some other representations. These are called Solomon modules, which are indexed by subsets of the Coxeter elements. And as an SN module, the homology is given by this formula. So this is the usual homology of a pair of the Z with the, where Z super T is the union of the Z sub SS as S goes over T. So in the previous picture, this is Z, this is ZS1, this is ZS2, and you take all possible subsets of of S1, S2, S3, and you will get an expression of the homology as an SN module now. And when I said that you can interpret the multiplicity as the homology or Betti numbers of some other pairs of semi-algebraic set, this is what I mean. The computing the multiplicities boils down to computing or knowing the dimensions of these homology groups. What are these things? So these are called Solomon modules. They have a definition which I will skip. Is very close to the definition of the usual spec modules in terms of row and column stabilizers of Young diagrams, except that instead of considering partitions where the parts appear in non-decreasing order, you should consider things called compositions, where the parts do not need to appear in non-decreasing order, and and then again there's notion of a column and row stabilizers and gives you these. Unlike in the spec module case, these need not be irreducible representations, by the way. So what with Cordian, we proved that there is though a connection between the spec modules and these Solomon modules, namely if the length of a partition is bigger than the cardinality of T, then in the decomposition of the Solomon module, which need not be reducible, the multiplicity of the spec module has to be 0. So there is a connection between spec modules and Solomon modules. And that really are the main parts. There are many other parts, but that's the main idea of how to get bounds and multiplicities. Okay, so maybe I skip to the next part, which might look very unrelated, but it is related. So this is work with Daniel Perucci, who's in Paris. And we are now looking at a very special case, forget symmetry for the moment. So we are looking at polynomials which are multi-affine, meaning that they are linear combinations of monomials in which square-free monomials. Of the monomials can have different degrees. So we can ask about Betti numbers of hypersurfaces defined by such multi-affine polynomials. And the surprising thing is, okay, so there's some motivations why multi-affine polynomials come up in practice, but maybe I skip this motivation. Yeah, very interesting. And here's which I find a little interesting. is that all these bounds on the Betti numbers are arbitrary semi-algebraic sets where of the form d raised to n, where d is a degree, n is the number of variables. But if you look at a hypersurface defined by a multi-affine polynomial, where the degree is d, then the number of connected components, only the zeroth Betti number, not the higher ones you don't know, can be bounded independent of n and just depending on the degree raised to d. And this bound is short because you can take a multi-affine polynomial like this and you get that. Okay. Now, I want to accept something about stability, and this is where the application of multi-affine is. So there is something in representation theory which you call representation of stability. So a basic example of representation of stability is the following one, that if you fix a, so I'm told that there should be some restriction. So maybe we assume that we have a compact manifold. So this is the configuration space of X, nth configuration space of X, which is just take the product of X n times and delete the diagonal. And then this configuration space, the homology of this configuration space is interesting. And it is known that if you take the pth homology for some fixed p, but n can grow, then this, the pth Betti number of the nth configuration space is eventually given by a polynomial in it. That's actually a polynomial. But you observe that this configuration space, so this is sometimes called the ordered configuration space. So it admits an Sn action, making this into an Sn module. And the homological stability, meaning this statement is eventually stable, is a consequence actually of the stability of the multiplicities of certain spec modules in this homology. So that whole area goes by the name of Fi modules. So there's a category of Fi sense of finite injective maps. And there's some very abstract theory that proves all the statements all at once. But I don't want to go into this. But what I want to talk about is that I want to interpret symmetric semi-algebraic sets as the number of variables go to infinity. So the standard way of thinking about it is that you look at the graded ring of symmetric polynomials in n variables, and then it has these maps, and you take the projective limit in the category of graded rings, and you have a notion of, let's say, symmetric functions, which are which you should think of as symmetric polynomials in infinitely many variables. And now, coming back to geometry, suppose if you have an ideal in this finitely generated ideal in this ring of symmetric functions. So then this ideal defines for every n via the limit map, via this map here. So for every n, you get actual symmetric polynomials in n variables, right? So you get real algebraic set in Rn, symmetric real algebraic set in Rn. And now if you fix a partition of some d, and then for n big enough, from this partition you can generate more partitions of n by adding a long row in the beginning. And so that defines a sequence of partitions generated by this lambda base n. So this is a standard way of going from fixed partition to a sequence in the asymptotic study of representations. And so this is what we conjectured with very sparse evidence, is that in that previous setting, if you have this notion of an ideal in infinitely many symmetric variables, look at this Vn, we can fix a partition and we can look at the multiplicity of a polynomial of some fixed partition, some pth homology, and as kind of analogous in the configuration space case, we will said that conjecture that this is eventually given by polynomial n. The evidence is very sparse. In fact, the only evidence at that point was this Boolean hypercube example. Because this, if you look at this polynomial in the lambda ring, as it's usually called, P4 minus 2P3 plus P2, so these are the Newton power sum basis of the lambda ring. So in fact, this V and I is given by this single equation. It's a calculation. And then we already saw that the multiplicity when I equal, so only the 0 at 1 appears and is given by this expression. And this right-hand side here is a polynomial. In fact, linear polynomial. Remember, the lambda is fixed. So that's an evidence in favor of our conjecture. But now with the multi-affine case, we have a little bit more epsilon more evidence, because if you take your generating function in the lambda ring to be a linear combination of the elementary symmetric functions. So then for each n, this is a multi-affine polynomial, multi-affine as well as symmetric. The previous example, there's just one ideal, but now we allow all possible, for every fixed D, linear combination, so infinitely many ideals. And then, so then we can prove that the conjecture still holds, that for if lambda is not the empty partition, then the multiplicity is 0. And if it is empty partition, then it stabilizes to not just a polynomial, but to an actual constant. Maybe I skip so this actually follows from two things, which I've both mentioned in the previous slide. So a key intermediate, so first of all, we are able to prove a monotonicity, that if M increases, then the number of connected components can only go down of that ideal. But the key intermediate step was thinking that, of proving this, is that each connected component is stable under the action of Sn. That means that Sn cannot permute the, or in other words, that the H0 is a multiple of the trivial representation. Now, the point here is that we already know from our bound on B0 of multi-affine hypersurfaces, never mind symmetric or not, that this H0, this B0 is small. It's independent of n, 2 raised to d minus 1. That means for large enough n, this there cannot be any other representations appearing in H0 other than the trivial of the sign. Because every other representation other than the trivial of the sign grows, this dimension grows with n according to the Frobenius formula. So in order to prove that this stability, that only the trivial can appear, you need to get rid of the case of the sign representation. But the sign representation has too many parts, right? Because 1, 1, 1, 1, and the restriction theorem that I shown earlier tells you that if you have a degree D symmetric semi-algebraic set defined by a polynomial of small degree, then multiplicities in the homology for partitions which have too many parts is 0. So this sign cannot appear. So this, so only the trivial can appear, and this proves this stability, and that is the key thing in proving the other inequalities. Okay, so I'm almost out of time. So I just want to mention that this limit, in the case where it's not necessarily 0, is not trivial. You might think that in this case, it will always get connected and it exists just because it's connected, but that's not true. That when this exists, it can be strictly bigger than 1. And the examples are quite simple. So if you take this symmetric function, then the limit you get 2 connected components. And if you take that one, you get 3. So it can be a non-trivial